Good evening, everyone. My name is P. Harshavardhan from Levy Institute of Engineering and Technology. During my internship at Emertxe Information and Technologies, I have developed I have developed an EV ADAS dashboard using STM32 Blue Pill, PicsimLab, and Python. Today, I will explain the project and its implementation and the results. Modern electric vehicles generate a large amount of real-time data, making it difficult to monitor everything manually. Our solution is an EV ADAS dashboard that displays vehicle parameters, detects collisions and blind spots, generates alerts, and provides live dashboard for better safety and monitoring. No system architecture. The system starts with sensors that provide input to STM32 Blue Pill. The controller process the data using EV control and ADAS algorithms and sends it through UART. Python dashboard receives this data and displays the speed, battery status, range, and safety information. This slide compares our simulation with real electric vehicle. Instead of expensive automotive sensors and CAN communication, we use potentiometers, STM32, UART, and a Python dashboard to simulate same concepts in low-cost environment. This project was completed in 9 phases, starting from software setup and peripheral configuration, followed by EV dynamics, ADAS implementation, fault detection, UART communication, and finally a real-time Python dashboard. We used STM32 Cube IDE for firmware development, PicsimLab for simulation, and Python for visualization. Timers were configured for scheduling, ADC for sensor inputs, UART for communication, GPIO for LEDs, and PWM for buzzers. The ADC reads accelerator, brake, and motor temperature values. The EV Dynamics module uses three inputs to calculate vehicle speed, torque, battery state of charge, range, and regenerative braking based on selected drive. Three ultrasonic sensors continuously monitor the front, left, and right sides of the vehicle. Based on obstacle distance, the system provides forward collision warning, blind spot detection, parking assistance, time to time to collision calculations for improved safety. System continuously checks for monitor overheating, low battery, collision risks, sensor failures, and communication errors. Depending on the severity, it generates advisory, warning, or critical alarms and safely stops the vehicle whenever necessary. The STM32 sends all vehicle and ADAS. The STM32 sends all the STM32 sends all vehicle and ADAS information. The STM32 sends all vehicle and ADAS information through UART every 100 milliseconds. The transmitted data includes speed, battery charge, torque, temperature, obstacle distance, alarms, and fault status for real-time monitoring. The UART shell allows us to test system by entering commands such as changing speed, battery level, temperature, driving mode, and fault conditions. This helps validate the system without charging hardware inputs. The Python dashboard receives UART data and displays it on speedometer, battery indicator, speed graph, EV information panel, and bird's eye ADAS view. This provides a clear real-time visualization of vehicle status. This project successfully demonstrated real-time speed and battery monitoring, collision detection, blind spot detection, motor fault handling, UART communication, and live dashboard visualization. The complete system worked successfully in PicsimLab simulation environment. Thank you for your time and common.h. This is the common header file used throughout the project. It includes all required libraries, utility macros, drive modes, and common definitions that are shared by every module. EV-control of minutes. This file defines the EV model. It stores vehicle parameters such as speed, torque, battery SOC, motor temperature, range, and regenerative braking. It also contains the functions that calculate vehicle behavior. Ultrasonic.h. This file contains the driver for HC SRO for ultrasonic sensors. It defines sensor IDs, distance limits, timing parameters, and functions to measure obstacle distance from front, left, and right sensors. ADAS.h. This file implements the ADAS logic. It defines alarm levels, collision warning thresholds, blind spot detection limits, and time to collision values to improve vehicle safety. Fault.h. This file handles fault management. It detects conditions like motor overheating, low battery, critical collisions, and it sets fault flags and places the vehicle in a safe state whenever required. UART shell.h. This file implements the UART command interface. It also allows to send commands such as changing speed, SOC, temperature, and resetting faults for testing and debugging. Main.h. This is the main configuration header generated by STM32 Cube IDE. It contains GPIO pin definitions, peripheral configurations, and project-wide hardware settings. Ultrasonic.c. This source file generates trigger pulses, measures echo pulse duration using timer 2, calculates the obstacle distance, and stores the measured values for ADAS module. Overall, the project follows a modular design. The sensor drivers collect the input data. The EV control module calculates vehicle parameters. The ADAS module analyzes the safety conditions. The fault mode monitors health system. And finally, the UART module sends all the process data to Python dashboard for real-time visualization. My project is an EV ADAS dashboard developed using STM32 F103 C8T6 Blue Pill, PicsimLab, and Python. The main objective is to simulate an electric vehicle and implement advanced driver assistance system features such as forward collision warning, blind spot detection, and parking assistance. The STM32 continuously reads inputs from simulated sensors like accelerator, brake, motor, temperature, and ultrasonic sensors, and it processes the data using EV control and ADAS algorithms, detects faults or unsafe conditions, and sends real-time telemetry using UART. A Python dashboard receives data and displays vehicle parameters such as speed, battery state of charge, torque, range, temperature, obstacle distances, alarms, and false status, and provides complete real-time monitoring and safe system similar to that used in modern electronic vehicles. The project starts by taking sensor inputs such as accelerator position, brake position, motor temperature, and ultrasonic obstacle distances. These values are processed by STM32 microcontroller. The EV control module calculates speed, torque, battery charge, and remaining range. At the time, at the same time, the ADAS module checks collision distance, blind spots, time to collision, the fault mode, continuously monitors system safety. Finally, all processed information is transmitted through UART to a Python dashboard where the user can monitor the vehicle in real time. ADAS is a collection of electronic safety features that continuously monitor the surroundings of a vehicle and assist the driver in avoiding accidents. Example like forward collision warning, blind spot detections, parking distance, automatic braking in emergency. In our project, I implemented three ADAS features: forward collision warning, blind spot detection, parking distance. Main objective of our project is to build a real-time EV monitoring and ADAS system. The EV metrics contains torque, acceleration, brake, MOT temperature, alarm, fault, signal. Mm, The torque value will be minus 40 Nm. Uh, Acceleration will be 67%, brake 72%, temperature is 28 degrees Celsius, fault 0, signal on. Uh, this is the speedometer. Uh, the battery health here is shown is 99%. This is the ADAS bird eye view. This is the speed history graph. If the vehicle is closer to us, then the alarm critical is shown and the warnings are sent. Here vehicle is far, so no warning is shown, and everything is clear and fair.